So welcome everyone to 60 Minutes in Space. My name is Mitch and I will be your virtual host this evening. Throughout the program, if you have questions or comments or things like that, you can type them into the chat. Our presenter will be keeping an eye on the chat so he may respond in real time. Otherwise, I will collect all those questions and we'll have time at the end for him to address those. And with no further ado, I would like to introduce Dr. Graham Lau from the Space Science Institute. Ta-da!
Thank you so much for the introduction, and hi everyone. First off, is my microphone coming through clearly? I think to better speak for the closed captioning, I'm going to use this microphone instead. I think this one actually captures the CC a little bit better. So hopefully everyone can hear me okay. I'm going to do my share screen here. So you should all be seeing my nice starry background on my computer monitor right now. All right, and we can get started. If I had to pick a title for tonight's 60 Minutes in Space, I would have called it this: Fireballs, Asteroid Rendezvous, and Vikings. Oh my. There's been a lot of really cool things happening lately in space exploration. Honestly, we could probably do 60 Minutes in Space every day and have easily enough material to fill 60 minutes worth. There's so many cool things going on in space science and space exploration and in our understanding of Earth all the time. But I do like when I speak for our audience our museum members and guests here in the audience, to speak a bit about Colorado. I know some of us here aren't from Colorado, so I'll talk a lot about some space things that matter to all of us, but I do like to focus a bit on Colorado. First off, some of you might have noticed this happening very recently here in Colorado. On the 2nd of October, we had a fireball just west of Denver, moving from the southwest to the northeast at 4:34 in the morning. And we live in an era where a lot more people have cameras outside of their houses. And so now we have a lot better videos. There are people out trying to track this fireball now to see if they can find some meteorites that might have come down to the ground. We don't know for sure if any meteorites came down from this fireball, but it's a very impressive sight to see. I wasn't awake when it happened, so I didn't see it. I know there were reports from folks in Wyoming and New Mexico as well. Did anyone here in the audience, by the way, you can go ahead and respond in the chat if you'd like. Did anyone here witness this fireball that happened over Denver this month? I can play the video again here while we give you a moment. I only see some no's coming in so far, so maybe none of the people who witnessed this or saw it on their cameras are in our audience right now, but you know, it's really cool to see these things in the sky. Most of you have most likely at some point in your life seen a meteor or a shooting star in the sky, but these ones are really, really bright. These ones are called fireballs. And so I'm going to move on here. Real quick, I think in the chat, we're going to drop a link if you're interested. There's a poster I'm going to talk through for a moment that shares some of the terminology around things like meteors and these fireballs like we just saw in Colorado in that video. So if you'd like, you can go ahead and click that link and that'll let you then, whenever you're ready, you can download the poster and see it much easier. But if we zoom into this poster, it kind of gives us some of the terminology because there's a lot of words around things like meteor and meteoroid and meteorite and all these things that can happen with things flashing through our sky. So first off, we actually have a large number of rocks and pieces of ice and dust in our solar system kind of just floating around out there. There's actually a staggering number of asteroids and comets in our solar system in two belts, as well as in a large spherical cloud. You know, we have a lot of these things that sometimes can even come pretty close to the Earth. Right now, we know of over 1 million asteroids that we are certain of, that we've identified. We know their orbits. We've tracked them. A lot of them have been detected by amateur astronomers who've helped out a lot trying to better understand where these things are. And of this very large group of over 1 million known asteroids, there's even tens of thousands that are called near-Earth objects or near-Earth asteroids. These are ones that can come fairly close to the Earth. They actually come past our orbit and cross over our orbit here in the solar system. And that might sound scary. There are so many of them. Most of them are actually pretty small. And sometimes they actually do come pretty close to the Earth, though. So very recently here, a little over a week ago, another asteroid, a near-Earth object, came very close to the Earth between the Earth and the Moon. However, that's actually a pretty far distance. That's 250,000 miles away. And so there's actually a lot of space between the Earth and the Moon. And so this asteroid that came close to us the other day, it passed 155,000 miles from Earth on the 17th of October. And it was an object that we actually know and it's been tracking for some time. That's maybe something like 20 to 40 feet in size. So like a small house. And I know that sounds scary, but these things actually happen really often. And again, there's a lot of space between the Earth and the Moon. This was actually the 106th flyby of an asteroid closer to us than the Moon this year alone. And so no reason to be scared. These things actually happen pretty often. We actually are trying our best. There's a lot of people out there in the world who are tracking asteroids to try to know when one of the big ones will come toward us. That said, there are some smaller ones that are in that size range of 20 or 30 feet that actually could be pretty dangerous for our planet. We had one come down not too long ago called Chelyabinsk, which I'll mention here in a moment. But yeah, we have a lot of these asteroids out there. We also have a large number of comets out there as well. You might think that there's like millions, hundreds of millions, billions of comets, and there might be, but we actually only have really good tracking and data for about 4,000 of them. And so we actually don't know them as well. We're pretty sure we know two major populations where comets are coming from in our solar system. One of them is kind of just beyond the orbit of Neptune and kind of in the same plane as the rest of the planets of our solar system. And then the other one is a big sphere of material called the Oort cloud, which we've never actually observed directly. We've just hypothesized its presence based on our knowledge of some comets. So some comets come very close into the solar system and back out in a very short time span, a few years to several decades, maybe even 200 years. But there are other comets that take thousands of years and even tens of thousands of years to come into the solar system and go around the sun and then go back out. And where they're going back out to, if we start tracking those trajectories, they're all going out to a rough region of space that's more spherical than the disk of our solar system. And so we have good reason to believe there's actually a large amount of material out there, even if we haven't measured it yet. And these comets, when they are traveling into our solar system, they make a really beautiful light display for us to watch. Their tails kind of going off behind them as they travel through our solar system, get heated up by the sun, blowing material off of them. They also leave a lot of material behind. And so maybe you've been fortunate enough to see some of the meteor showers. We have annual meteor showers that happen at regular times in the Earth's orbit around the sun. And that's because what happens is the Earth actually travels through a band of dust and ice left over by comets. And some of these annual meteor showers, we actually know which comets it was that caused that. And so unfortunately, we don't have any major upcoming meteor showers that we can watch. One of my favorites of the year is the Leonids that comes up in November. Unfortunately, this year, the moon is actually going to be out most of the night during the Leonids. And so if you're interested, on the morning of the 17th of November, in the very early morning, an hour or so before sunrise, maybe 2 hours before sunrise, you might be able to see a nice light display of a meteor shower. But it's going to be a little bit of a wait until we have another really good one. But we have lots of material constantly falling on our planet. Each year, something like 40,000 tons of material falls onto the Earth from space. But most of that material is ice grains left over by comets that burns up right away, or small pieces of rock that burn up right away. And I do want to answer a question right now. I see Adam Heavener asked in the chat if the James Webb Space Telescope will be able to see the Oort cloud. And the answer to that is no. James Webb isn't really made for resolving something like an Oort cloud object that close to our planet. So James Webb is going to be using infrared and looking out into the universe to better understand things. It will do some inner solar system stuff, looking at some planets, but it's mostly designed to be looking at galactic objects, extragalactic objects, and things like exoplanets. And so I'll mention that towards the end of tonight. But like I mentioned, we have lots of stuff falling on the Earth all the time, and most of that stuff burns up. And so what we see in the sky as a shooting star or a meteor a lot of times it's just a small grain of ice, maybe a small pebble's worth of rock that's burning up, and it's usually 60 miles or so above our head. So when you see a shooting star come down, it might feel really close, but it's actually pretty far away. I see another question coming in from Karina about how fast asteroids travel. These are what we call hypervelocity. They're traveling much faster than almost anything we can make on the Earth. We actually have laboratories at places like NASA where we build giant guns with the intention of replicating these hypervelocity impacts. And so we'll use like giant magnets and things to shoot little marbles of metal into rock and see what happens. But even then, we're not getting close to the thousands of kilometers per hour that these things are hitting. They're traveling very, very fast, which is why when they actually do hit the Earth, and if they're very big, they can actually cause a fairly large crater to form in the Earth. Places like Meteor Crater in Arizona, we see them all over the place, but on Earth they erode. And so I'll discuss the moon and some craters here in just a moment. I see a question from Tabitha, why would we use magnets to speed something up? In this case, it's because we're using things like metal that's already magnetic, so that we can actually make it move faster. We can use magnets and a magnetic field to push that metal along because it's magnetic. And so we'll use magnets to basically shoot these things as fast as we can. Now that said, what we just saw in Colorado, or what I guess none of us saw, but what a large number of people had recorded on their cameras was what we call a fireball. Now there's different uses of this terminology in space science, but in general, a fireball has to be at least twice as bright as Venus. Sometimes people say just brighter than Venus. Some say twice as bright, as usually the one that I hear is the rough rule of hand. So to be a fireball, it has to be really, really bright. And then something else can happen too. You can see here something called a bolide. And so a bolide is what happens when one of these large comets or asteroids or materials actually explodes in the atmosphere. And often that explosion can make a sound too. And so usually you'll hear the sound of a bolide. I'm just realizing I should have put a video in of the Chelyabinsk impact, because with Chelyabinsk, what happened in Russia, I want to say it was in 2013, there was a giant bolide, we call a super bolide, exploded in the atmosphere right over this town in Russia called Chelyabinsk. And when it exploded, it had enough pressure of the explosion to blow glass out of windows of buildings and knock people off of their feet. It did send several people to the hospital for various injuries that occurred because of this. And a lot of meteorite hunters have gone and found many of the pieces that blew off of this bolide. So it was a very large impactor or a structure that blew apart during this. And then we get lucky. Sometimes for people like myself who love meteorites, some of these things fall to the ground. And that's what this term is here at the very bottom. A meteorite is any of these materials that actually falls down and hits the Earth. Now, most of the time, they actually fall into the ocean. If you think about the size of about the structure of the Earth is 70% ocean. And so most meteorites hit the ocean, they sink down to the bottom of the ocean, they get covered in sediment and debris, and then eventually they get cycled into the mantle of our planet. And so most of them aren't really accessible for us. But we do have the fortune of going out and finding meteorites in various places. Hopefully you can see my camera well. I'm going to actually hold up 2 meteorites right now. And I guess technically I'm holding up 3 since my wedding ring is also a meteorite. But first off, there's this meteorite I'm holding towards the camera. Hopefully you can see it well. Let me know if you can't in the chat. This meteorite is an iron nickel meteorite. It's composed of 2 minerals, really, camosite and tannite, that are making that kind of zigzagging pattern. You can kind of see these little lines in this meteorite here. And these lines are these 2 different minerals that really only form in space as the iron and nickel are cooling very, very slowly as these things are cooling down. And what these things represent is actually the cores, or the interior molten metal of planets or planetoids that existed long ago and then broke apart and had a bunch of their pieces get dumped out into space. And then we have a chance to find some of them. But there are other kinds of meteorites out there as well. Now, those iron nickel meteorites are really, really easy to find because we can use metal detectors and we can look on the ground to find them. They're very magnetic. my wedding ring is very magnetic, and so I can hold a magnet near it and pick up the magnet with my wedding ring. But other meteorites aren't as magnetic, and they're much harder to find. Meteorites like this one. This is called a chondrite meteorite. The word chondrite comes from the ancient Greek word for a berry or a grain. These chondrite meteorites have little flecks of metal in them that formed in the very, very early solar system. I do want to just pause for 1 second to answer a question. I see Charlie, who's 5 years old, wants to know why the bolide explodes when it's coming down in the atmosphere. And so what's going on there, Charlie, is that as these large structures come into our atmosphere, some of them might be just solid pieces of metal like this meteorite, but then some of them are piles of rock and rubble. Sometimes they're even cemented together by ice. If they're cometary materials, it might be a bunch of ice and rock and dust pushed together. And so when it's heating up and coming down through our atmosphere, sometimes parts of it will heat up a little bit faster than other parts. And so the part that heats up really fast can explode and blow the rest of it apart. And so that can lead to a bolide. It's really because it's hitting our atmosphere, it's causing a lot of friction and heat. This is what happens when something starts rubbing against something else. And so these rocks start rubbing against our atmosphere, and it makes them get really, really hot. And then they can actually get really, really, really hot and explode. And I hope that's not too much of a definition. Hopefully your parents can help you a little bit there. But back to meteorites. So like I mentioned, we have things like these chondrite meteorites, and they're actually pretty hard to find. If you go out just like in the woods looking for something, you could take a metal detector and look for iron nickel meteorites, but you might miss a chondrite meteorite or another stony kind of meteorite, especially once it falls down onto the ground and sits for a while. It'll rust at the surface, it'll get dark at the surface, and it'll look like any other rock. There's actually a pretty good chance that at some point in your life, you've walked over top of a meteorite and you didn't even know it because it looked like other rocks around the area where you were walking. And so for that reason, there's two kinds of places on Earth where a lot of people want to go. I have another fun question from Sydney, who's 7 years old. Sydney wants to know if this is how I found these meteorites. Unfortunately, no, I did not find these meteorites myself. I purchased these two from collectors. I would love to go out and do some more meteorite hunting. I haven't had any luck yet. I do have a metal detector, and so I've been trying, but it is difficult to find them. And part of the reason for that is because of these two really good places to go to look for them. One of those places is to go to a desert, a place especially where there's a lot of sand, because you might find a meteorite because it'll stick out in the desert and be very unlike the other sand and perhaps rocks around it. But one of the best places to go on Earth to look for meteorites is also a pretty cool place to go and look for penguins. So Antarctica is a great place on Earth to go to find meteorites. And it's actually the place where we've found the most meteorites so far, because every year during the Antarctic summer, NASA has a program called ANSMET, where researchers, scientists go down and they drive around on snowmobiles on the ice in Antarctica, and they've slowly been mapping out all of the meteorites and collecting them. And because of that, we have tens of thousands of meteorites they've collected over many years of doing this. Some of our best meteorites have come from this. Two reasons that it's nice to look in Antarctica. One is that it's ice. There's lots of ice everywhere, so it's very white, very easy to see a dark rock if it's sitting on top of the ice. But also, again, you can really easily find things like those chondrite meteorites and stony meteorites because they'll stick out just as well as one of the iron nickel meteorites. And so it's really, really easy to find those in Antarctica. Another question came in, one from Emily. Emily wants to know what was the asteroid that killed the dinosaurs called? We don't actually have a name, like a good name for that impactor itself, but we do have an area where we think it hit the Earth in Chicxulub, off the coast of the Yucatan. It's just to the north of the Yucatan Peninsula in Mexico, is a region where we're pretty sure that that large body hit the Earth that caused the end of the Cretaceous and the beginning of what we call the Paleogene, that also marked the end of the dinosaurs. There were a lot of other things going on geologically then, but we're pretty sure that impact was the major thing that really caused the demise of the dinosaurs and lots of other living things at that time. So now back to this idea of meteorites. I wanted to share briefly things like that Chondrite meteorite are actually pretty important for our understanding of our solar system because they have some of the oldest materials in them from our solar system and even from before our solar system. So about 4.567 billion years ago, this giant gaseous cloud of dust and ice started collapsing and making our solar system. It made our sun, it slowly and eventually made the planets. And as this was starting to happen, a lot of things got very hot and melted inside of this basically disk of material around the early proto-sun. And as things were starting to cool down, the very first things that were becoming solid can actually be found inside of chondrite meteorites, just like this one that I have here in my office. So those things are called calcium aluminum inclusions. They're these little grains that we can find inside of these chondrite meteorites that are the very first solid things that were forming in our solar system. And then later we had these things called chondrules forming. The chondrules are these little kind of metal circles, metal flecks inside of these meteorites. They are basically what ends up eventually forming those core materials. The iron nickel meteorite is made from a bunch of these chondrules that eventually melted inside of the core of an early planet to make its inner core of iron and nickel. I have another question from Aiden, age 9. Do some meteorites have liquid? That's a very good question. There's different kinds of things we can find inside of meteorites, including things like what we call hydrous minerals. These are minerals that have water locked into them. And so there are some watery stuff inside of them. And so sometimes we talk about watery asteroids, watery meteorites, things that were delivering water to the early Earth, but not really much liquid. So this was a time when anything that would be like a liquid, like you think of like water or methane or ammonia, these things were very, very gaseous in the inner solar system. They actually ended up forming the larger planets like Jupiter and Saturn and Uranus and Neptune. Those larger planets sucked in a lot of that, what we think of as liquid, all that water and ammonia and those kind of things to make themselves so huge. But back in the early solar system, we also had something else inside of these meteorites that really fascinates me a lot. So these chondrite meteorites, one reason I love to collect these is because there are solid minerals inside of these meteorites that come from other solar systems from very, very long ago. And these things are called pre-solar grains. These are small grains of material inside of only chondrite meteorites. It has to be these really old meteorites that have the oldest materials that haven't melted yet, like those iron nickel meteorites have. These meteorites can have some of these grains inside that came from other star systems long ago. When stars exploded in supernova and blew their material out into the galaxy, some of that material came to our solar system and some of it didn't melt with the rest of all the material around the sun. Some of it actually got locked inside of those meteorites. And so I'm going to do a little bit of chemistry here. So for our younger people, this might be a little hard to follow, but there are different kinds of each kind of element, and they're called isotopes. So here's two isotopes of carbon. One is called carbon-12, one is called carbon-13. They're very similar that they both have 6 protons, but carbon-12 has 6 neutrons, while carbon-13 has 7 neutrons. And this makes them, they're very similar. They're both carbon, they both act like carbon, but it also means that they're slightly different in the amount of material they have and the amount of mass that they have. And so on our planet and in our solar system, the amount of carbon-13 and carbon-12 that we have in our solar system, it was locked in place when our sun was forming and our solar system was forming. And it actually got locked in place at just about 90 times more carbon-12 than carbon-13. However, this is not necessarily the case for other solar systems. And so it's a really cool feat of science that we discovered that those pre-solar grains really do come from other star systems by measuring the carbon-12 and carbon-13 inside of them. And so here we have a silicon carbide grain plot. Here we have graphite grains in a plot. And what you can see that this blue line that's going vertical here, this blue line is roughly 90 times the carbon-12 than there is carbon-13. And what this is showing you is that in these grains we find that we call pre-solar grains, sometimes there's way less carbon-12, and sometimes there's even way more, 100 times more carbon-12. And so that's how we know that these did not come from our solar system. They didn't get melted and didn't get reformed with everything else that made the early solar system. And so it's really important for us to have things like pre-solar grains and chondrite meteorites to study. And I'm a meteorite collector, I love them, but it's also nice for us to go out into the solar system with our spacecraft and actually go look at some of these asteroids and comets. And we've been doing just that. And actually just this month, on the 16th of October, we launched a new mission going out to some new asteroids. This one is called Lucy. It's actually named after a human fossil, a hominin fossil called Lucy, which itself is named after a Beatles song. Lucy is going to travel to a certain kind of asteroid called a Trojan asteroid. It's actually going to fly by 6 of them. The Trojan asteroids are pretty cool. I will mention, if those of you who are following the news might have heard that Lucy, right after launch, one of its solar panels did not fully deploy. They are currently working the problem. They've said that even if they cannot get the solar panel to latch, that they are still getting roughly 90% of the expected power. So even if it is not fully deployed, they think it's mostly unfurled. But they are working right now to figure out if they can actually redeploy and try again to get the solar panel locked in. I see one of our viewers mentioned in the chat that they actually watched the Lucy launch from Florida. That's fantastic, Archer. I wish I could have seen it. I imagine it was beautiful. And like I mentioned, Lucy's going to travel to these special asteroids called Trojans. So this GIF image here shows our inner solar system with Mercury, Venus, Earth, and Mars orbiting really quickly around the sun. And then we can see out here Jupiter is this brown dot, and traveling along with it, both before in its orbit and after in its orbit, is these large clouds of material. These are the Trojan asteroids. These asteroids are in a special gravitational dance with Jupiter and the sun that allows them to stay stable right there. And so we're going to go out and actually measure these for the first time ever. We know that they exist. We've seen a bunch of them, but now we're going to send Lucy out to actually travel to them. And Lucy's flight path is actually really cool. So Lucy is going to go and do 2 small orbits around the sun and the Earth together. It's going to come back really close to the Earth so that it can use the Earth as a slingshot to give it even more speed. And so it's going to do that twice, come back around. On the second time, it's going to leave the Earth and it's going to travel out. First, it's going to make a stop at one of the main belt asteroids. So this is the main asteroid belt between Mars and Jupiter. It's going to go right past one of those first. And then after about 6 years of traveling, it's going to get out to the first set of Trojans called the L4 Trojans right in front of Jupiter in its orbit. It's actually going to fly past a few of them there. And then this is really cool. It's going to come back around again in towards the sun and the Earth. And then it's going to travel back out to the L5 Trojans. And it will finish its expected mission duration at one of these L5 Trojans. So it's actually going to visit the region of Jupiter and come back to the Earth, which by itself means that this will be the very first spacecraft to ever go out as far as Jupiter and then come back again. And so this is already pretty huge. It's got a lot of really cool instruments on it as well for measuring the surfaces of these asteroids, for learning more about them. We also have some other missions out there. One came back fairly recently. One is on its way back. These are the Osiris-Rex mission from NASA here on the left, and the Hayabusa 2 mission from Japan, from the Japanese Aerospace Exploration Agency, or JAXA, on the right. Hayabusa 2 came back just this past year in December, and they've already been analyzing material from an asteroid called Ryugu that this craft sampled. And then Osiris-Rex is actually traveling back to Earth right now. It just left here recently, earlier this year in May. It'll get back to Earth in 2023. And then we're going to have a bunch of material from another asteroid called Bennu to study. And by studying these asteroids, we learn so much more about the history of our solar system, the formation of planets, various processes that occurred through our solar system over time. We have another cool upcoming mission called Psyche as well. So I mentioned earlier that I have this iron nickel meteorite, and it represents the core or the interior of an ancient world from long ago that has long since blown apart by collisions in our early solar system. Well, this asteroid called Psyche from our detections so far, our knowledge so far, it looks like it's entirely iron nickel. It's a very big chunk of metal as an asteroid in space. And so the Psyche spacecraft is going to fly out to this asteroid and study it and learn a lot more about things like how those early planetoids were forming and being destroyed, about the composition of that material. There's really a lot of really cool things for us to study. Also, for any space nerds here, this will be the very first spacecraft to use a new kind of communication system called the Deep Space Optical Communications, DSCO. This will be the first time that instead of using radio waves to send a message back to Earth, we're going to send signals of light back to Earth, because we can actually put together a lot more data in a light packet than we can in a radio wave packet, and send a bunch of photons back. And so they're going to try this for the first time with Psyche. So that's pretty cool. And so there's been a lot of really cool stuff going on with asteroids lately, but maybe you've been following the news on space. There's some other cool space news. Recently, the Chang'e 5 lunar rover from China returned some sample back to Earth from the moon. We're still learning so much about the moon. We know that not long after the formation of the Earth, the moon formed. And we know that when we look at the moon from our side, from the side that faces us here on Earth, we can see like two real kinds of different textures of the moon. There's this light colored material. It's more white, gray kind of colored. It's much higher in elevation. It has a lot more craters in its surface. And then we have this darker material here that we call the mare, which stands for sea, like a sea of water. But in this case, the mare are seas where lava flowed long ago and made these giant seas of lava on the surface. And up until now, we thought that it was about 2.8 or 2.9 billion years ago when was the last time these mare were forming. But the Chang'e 5 rover landed up in this region on the moon and took some of these samples from the mare, from what we think were the youngest exposed rocks that we could find on the near side of the moon. And those samples came back, and a few papers just came out this month. 3 of them in the journal Nature, 1 in the journal Science, another in the National Review from Oxford, showing that the ages they found for these rocks are fairly well mapped to about 2 billion years old, bringing the period of volcanism, of volcanoes erupting and forming this lava on the moon, about 800 or 900 million years closer to now. And that means that the surface in some of these areas in the mare is actually much, much younger. I have another fun question I just saw in the chat. I do apologize, and there's a lot of questions coming in. I'm trying to keep up, but there are a bunch of them, so I can only read a few at a time. But I do see, so Aubrey, age 11, wants to know if we've ever predicted that there was water on the moon. Aubrey, yes, we've actually found water on the moon. We found water in regions of craters that aren't exposed to sunlight. So there are some craters on the north of the moon and the south of the moon that never really get fully sunlight on them because they're little kinds of mountains on the edges of the craters. And so some parts of them stay in shadow all the time. And we've actually measured ice there. We also some years ago had a mission called L-Cross, which was like a big bullet. The rocket turned into 2 different pieces. One was a giant bullet, and the other one was an instrument that flew in behind it. And we took the bullet and we shot the moon with the bullet. And then the one that flew in behind it measured the material coming out. And we actually measured some water there as well. And so we know that there actually is some water, not only as ice on the moon, but there's also water bound up in the rocks of the moon as well. But that's a very good question. But yeah, so these findings from Chang'e 5 that were just released, they actually teach us that there's a lot more going on with the moon than we thought, that the volcanism was happening a lot longer than we thought. And for anyone interested later who wants to stay after the show, there's actually a bit more depth of the science. We actually had 2 main hypotheses for how these mare had formed later in the moon's evolution. And there's actually some really cool data that now makes us have to go back to the drawing board, frankly, because the findings actually kind of make both hypotheses not really seem to fit anymore. But just to make sure that we're still moving along, there's still some really, other really cool stuff to talk about. One, the moon is really awesome and we want to go there. We had humans on the moon a few decades ago, and a lot of us now want to know, will we send humans back? And that's part of NASA's current mission. is the Artemis program is to send humans back to the moon. Now, there's a lot of really cool stuff going on in human space exploration right now with SpaceX and Blue Origin launching people. An actress and a movie director just went to the International Space Station on a Russian spacecraft to create a movie. A lot more people are getting interested in going into space. But we also still have a lot of human exploration to do, and Artemis is part of that program. And what just happened here the other day, on the 21st of October, is we had the very first complete stacking of the Orion spacecraft on top of the Space Launch System rocket, or SLS, which is called the Artemis 1 mission. Now that they've stacked it together, they're going to start testing for the next several months with the hope of launching in February 12th, a mission that's going to go out to the moon. And so, like I said, so a series of tests are coming here. They're planning on launching in 2022. This is a non-crewed mission, so no humans. I see a typo in my writing here. So no humans are going to be on board this one, but it's going to go out to the moon. And if any of you are interested, we can actually share a link right now in the chat for a really cool YouTube video from NASA visualizing the launch of Artemis 1 here in February. It's going to go out to the moon and do a big loop around the moon and then come back to the Earth. It's going to land in the ocean, and then a Navy ship is going to pick it up. It's a very big test for us to actually test the whole system to see if this is ready to send humans to the moon. Now, if we do have any young explorers here amongst us, maybe young people who want to become astronauts eventually, or maybe you want to build robots. I'm the director of an undergraduate student competition to build Mars rovers, and students bring them to the desert in Utah and they compete. There's also something called NASA Lunabotics, where college students can build lunar rovers and take them out and compete in a lunar setting that NASA creates for them. But something else just came up that's very new, is Lunabotics Junior. So this contest was just announced for American school students from grades kindergarten through 12th grade. There's actually two age groups. It's kindergarten through 5th grade, and then 6th grade through 12th grade are going to have the chance to compete and submit their idea for what a really cool lunar robot might look like. And so you'll have to submit a drawing or a design of your robot. You'll also have to submit an essay of why you think your robot would really be great, and maybe why it would work well for learning more about the moon. This is being run by the group called Future Engineers. They're the group who recently had the Name the Rover competition, which is how we named the Perseverance rover. I was a judge for that competition. I think I might be a judge for Lunabotics Junior as well. I'm very much looking forward to how many of our young people in this audience might be interested in applying and competing. Those who win will get some really cool virtual classroom visits from some people from NASA who lead places like the Kennedy Space Center in Florida. So hopefully some of you are interested in that. It should be a really cool competition. But let's kind of use some space now to talk a little bit about Earth. And those of you who maybe know me or have seen me online know that I always have a picture of Earth somewhere in my talks. I love our planet. It's my favorite planet. But I also love a lot about our history. And it's one reason I love our museum. DMNS has a lot of really cool exhibits, some permanent, and then some temporary exhibits that allow us to bring to Denver, to bring to Colorado, just some really cool information about culture, science, history, the knowledge we have about who and what we are. And one of those really cool recent exhibits that we had, it's no longer at the museum, but we had it back in 2017. It was called Vikings. And maybe some of you here had a chance to visit the museum during that time. It was the largest collection of Norse Viking Age artifacts brought to America for this exhibit. It was called Vikings, Beyond the Legend. It was put on by DMNS in collaboration with the Swedish History Museum, as well as museum's partner in Austria. Now, the Viking Age was an era from the years 750 through 1100, where the Viking peoples, these Norse peoples, and the job of being a Viking, of going out on a Viking, a raid, was very common amongst their peoples. And they actually traveled a good part of the world. They traveled to the British Isles. They traveled to Iceland. They traveled to Greenland. They traveled down to the Mediterranean and visited Africa and went into France and other countries. They went over through Russia and Estonia and Latvia and Lithuania. The Vikings traveled a lot, and they took a lot of culture with them as well, which is why a lot of us are very intrigued by them, is that they kind of spread their culture out in a lot of places. And one place that they went to was North America. We actually now know that long before Columbus and other Europeans of that era were coming to the Americas, that Vikings had come over from Europe as well, from Iceland, from Greenland, from Sweden and Norway. But recently, you might have heard this paper, it just came out about a week ago, that we have a new age date on one of the best known Viking settlements in North America. And so that settlement is called Lancel Meadows. Lancel Meadows is a settlement in Newfoundland. You can kind of see on this map down here, it's a region showing over here is Europe, the British Isles, you can see Scandinavia, and then Iceland, Greenland, and then you can see over here is Canada. The Canadian islands are up here, the Northern Archipelago is up here, and then down here is Northern Canada with Newfoundland, and there in this little black square in this map, if you can see that, is Lancel Meadows. This is where a very large Viking settlement is at. It's a UNESCO heritage site. It's been very well studied because of the presence of a lot of Viking artifacts, of artifacts from Norse peoples who traveled here many hundreds of years before other Europeans had started traveling to the Americas as well. They found lots of samples of Viking artifacts. They've also found samples of pollen and other botanical signs of evidence that these Vikings and these peoples who were inhabiting the settlement were also traveling much further south into the Americas as well. And we know from one of the Icelandic sagas that there is a story of these Norse peoples meeting some other kinds of peoples. They never really explained it very well, but we're pretty sure that it's a story of these Norse peoples meeting some of the First Nations peoples of Canada. So some of the indigenous Native Americans who lived here long before any Europeans came over, that there was an interaction between those peoples recorded in this saga. Now, this new research uses something called radiocarbon dating to look at the process that could allow us to understand the date. Radiocarbon dating is a process that really ties us to space. So we constantly have energy, materials, radiation coming from our sun and from the galaxy, coming down into our atmosphere. And sometimes some of those high energy things, like maybe a neutron has a lot of energy, it can hit an atom like nitrogen-14, and it can actually turn that nitrogen into carbon-14. And so it's actually changing the element from nitrogen to carbon. It's transmuting the element, really. And it's part of why we are not just star stuff. We are star stuff, but we are so much more. We're star stuff. We are cosmic ray stuff. We're also atomic bomb stuff. If you blow up an atomic bomb, it also causes nitrogen-14 to turn into carbon-14. And all of us right now have some residual carbon inside of our bodies that was formed from nuclear bomb testing. But this process forms this carbon-14 that can then go into carbon dioxide. And it can be inhaled by trees, by plants, that then can be eaten by us. And so all of us right now, we actually have some amount of carbon-14 inside of our bodies that came from this process coming from space. One of our audience members, Mai, just said everything is connected. And that's exactly what it is. We are all connected. We are at all times connected to each other, to our planet, to the cosmos. And it's really beautiful to think about. Now that carbon is actually radioactive. So it's okay inside of your body. It's not going to hurt you. But after things die, so like when animals die or trees break down, they stop taking in fresh carbon-14. And so the carbon-14 that they had starts to break down and decay and becomes nitrogen again. And so we can actually use that process to measure how long it's been since something was actively alive or something was formed, which is actually really important for archaeology and paleontology. Carbon dating is really good for measuring things that are like 40,000 years old or less, or even things sometimes up to 100,000 years if we have the right instruments. It's a little bit more expensive and takes more work, but we can also look out to about 100,000 years of carbon dating. This is how, for instance, we've measured some of the oldest things on the planet. I love this picture so much. It's one of my favorite of bristlecone pines out here in the American West. Bristlecone pines are the oldest known single trees on the planet. The oldest one is over 5,000 years old. It's 5,067 years old. And so it's really cool. We can use carbon dating to measure the age of the carbon that was formed inside of this from this radiocarbon. But it doesn't always give us the best answer because some things change through time. I mentioned atomic bombs. they cause an increase in the amount of carbon-14 that we get in our bodies. We can actually measure the decrease in carbon-14 through time to show us when we have the bomb spike in 1965 to 1968 from bomb testing, because it's changed so much. But we can also have something like a massive solar flare or a solar eruption can also cause a slight change in how much carbon-14 is being formed at any time. And that's what happened with this new date for the Viking settlement in Newfoundland. So we know if we go to trees all around the world, we can actually measure not just the age of the tree, but we can actually measure each of the tree rings themselves. And we can measure each year how much carbon-14 that tree was getting. It allows us to better calibrate our models of how we can use carbon-14 for dating. And it also tells us when there's big spikes. And there was a big spike in the year 992 to 993 from a solar storm that was producing a lot of extra radiation. That radiation caused a big spike in carbon-14. And so what these researchers in this recent paper that came out last week did is they looked back through the growth rings on side of pieces of wood at the Viking settlement. They looked at 3 pieces of wood that still had bark on the outside. So you have to have the bark so you know where the end of the tree rings happens. And then they measured down through the tree rings, and it took 29 rings on all 3 samples to get to the spike from the year 992 through 993. And that shows them that if they add 29 years, 1 for each ring, they get the year 1021 for the time that this wood, that these trees were harvested to make this settlement. And so that's exactly 1,000 years ago. I see another fun question I'm going to answer real quick from Karina. Karina wants to know, how can we measure how old rocks are? Karina, we actually have a lot of different methods for measuring how old rocks are. It's kind of similar to using carbon-14, but we actually have other things that last a lot longer. So carbon-14, it actually breaks down really quickly, which is why we can only use it for 40,000 years. It doesn't last very long. But some rocks are billions of years old. They're 2.5 billion, 3 billion years old or more. And so for us to measure those, we have to use something besides carbon. And so for that, we use things like uranium and thorium and lead. There are other elements out there that we can actually use to measure in a very similar way the breakdown of radioactive elements. And it teaches us how long these rocks have been on the surface of the Earth. We can also measure the cosmic ray bombardment of the surface after a glacier recedes. And it actually tells us how long it's been since a glacier existed in a certain region. It's how we know how the ice ages, how far glaciation made it on Earth in the ice ages. That's a very good question. But yes, this is a very cool finding. I do realize we're getting close to the end of our hour here. I do want to just share just a few more things real quick, and then I'll take any questions you have. One thing you might have heard of here very recently is the announcement from Blue Origin, the space company that's been launching some people to space very recently, including William Shatner. Blue Origin, along with several other groups like Boeing, Genesis Engineering, Redwire Space, Sierra Nevada Corporation in Nevada, they've announced a partnership within the next 5 to 10 years to build a new space station that they're calling Orbital Reef. The plan for Orbital Reef, which you can find out more at orbitalreef.com, is a space station that will work like a business park, basically allowing 5 to 10 people to do business in space. There's some other space stations in planning too. There's Starlab from NanoRacks is planned for 2027. There's also a plan from Axiom Aerospace to launch some new modules to the International Space Station in the next few years that can then also de-dock from the space station and make their own space station eventually too. So these are some cool things. So there's a lot of really cool space exploration going on in understanding the history of Vikings on Earth and understanding the asteroids of our solar system and sending humans to space. One more cool thing we might have read about very recently, we just had what might be the first detection of a planet from another galaxy. So right now, there's a few ways that we can find planets around other stars here in our galaxy. And one of these ways is called the transit method. Basically, if we stand right between us and the star, and a planet goes in between that star and us, sometimes it'll block out the light of the star. If it passes right in front of the star, it'll block out the light from the star, and it tells us there's a planet there. That's called the transit method. Well, very recently, some astronomers have announced that they did something very similar using X-rays. and a transit method, and they think they found a planet in the Whirlpool galaxy 23 million light years away. That means that the light that left that star that tells us that planet could be there left 23 million years ago. So that's pretty cool. I am going to finish here in just 1 minute. Really quickly for everyone watching, if you are interested, I thought I'd share 2 more things that are coming up very soon. One of them is tomorrow at 5 o'clock Mountain Time. The Lunar and Planetary Institute is going to have some astrobiologists and astronomers on to talk about our salty solar system, brines, salt water in our solar system, not just on Earth and our ocean, but on worlds like Europa and Enceladus, maybe even something about Ceres and Pluto and Titan. I'm not actually sure what all they'll talk about, but it should be a very fun meeting to talk about salty water in the solar system. And then also here very soon, we had a question earlier about James Webb. There's an upcoming meeting here on Saturday at 2 o'clock Mountain Time. This is Central Daylight Time. It's 2 o'clock our time. There's going to be a meeting with planetary scientists to talk about the James Webb Space Telescope and what all it's going to be looking for and finding. And so with that, I will stop my presentation. It's been such a pleasure having this time to share some really cool space things with you, some recent research, and new things we're learning. I saw that we had so many questions in the chat. I'm more than happy to take any of your questions right now. We can talk about all kinds of cool things, radioactivity, asteroids, meteorites, fireballs, whatever you're interested in space. I'd love to hear your questions. Oh, Mitch, I think you might be muted there.
Thank you. I was saying thank you. What a great presentation. And we do have lots of questions in the chat, but also this is a great time to put in any questions you've ever had about space science in the chat. A lot of people
I
are
see
wondering
one right away, actually. I see this one from Emily. I think she asked it more than once. So Emily wants to know if we can hear sound in space. This is a really good question, Emily, because you might have heard that like no one can hear you yell when you're in space. So space is what we call a vacuum. There's not a lot of stuff. There's actually almost no stuff in space, which is why we call it space. It's actually so little amount of stuff in space that our best vacuums on Earth. So we make vacuums to try to suck the amount of stuff out of an area so we can do cool science. And even then, we cannot make a vacuum as good as space makes a vacuum. And so there's just nothing there for sound to move through. So the way sound works, so when you're hearing with your ears, I mean, we have evolved really cool way of hearing movements in the air, which is what sound is. You're hearing movement in the air. If I snap my fingers, that sound, I produce that snap. What I'm really doing is I'm causing a small displacement, a movement in the air, and then air is moving. There's vibrations in the air. And as it comes through the air, it hits my ear. And the biology, the structure of my ear allows me to take those waves, that movement of the air, and turn it into sound so I can understand what it is. And there are different kinds of hearing on our planet. So we have a very specific range of hearing. We humans, we hear about 5 waves per second. So 1, 2, 3, 4, 5 per second, up to 20,000 waves per second. I can't wave my hand that fast. It's very fast. 20,000 times per second, a wave can hit your ear. And it sounds really, really high pitched. But like dogs, my dogs can easily hear up to 50,000 waves per second. There's even things like dolphins and bats. They can hear well over 100,000 waves every second of sound hitting their ears, and it's how they evolved too. But in space, there's nothing like the air around us. So all this air around us is actually a bunch of molecules. Right now, you're breathing in this world of molecules around you, and they're coming into your lungs and back out again. They're touching you, they're touching the walls, they're touching all of us. But in space, we don't have as many of those molecules. There's very, very few of them. And so there's nothing for sound to move through. And so if you ever watch a movie of astronauts in space, if they do a really good job, you won't hear anything in the space environment. But you might notice when the astronaut has a helmet on, if they like clank their head against the space station, they'll hear a noise because they'll hear the clank of the hood transferred into the air of the spacesuit going to their ear. But otherwise, no, we can't hear sounds in space. And so we use other things to try to hear. or see. We can use things like visible light. We can also look at things like other kinds of radiation around the world, and we can actually turn that into sound in a process called sonification. We can take the data we have from our spacecraft and we can turn it into sound and into images to make it easier for us to understand. If you're interested, I highly recommend looking up sonification, especially for space data. There's some really cool videos out there of that.
Amazing. We've had a lot of people wondering, what's the largest meteorite to hit the Earth, and what's the largest meteorite you've ever seen?
Okay, so there's a couple of good questions there. So first off, the largest meteorite to hit the Earth, I actually do not know the answer. And I'll tell you why. So like I said, with the moon, we see craters all over the moon. There's lots of them. We can see craters that formed on the moon not long after it formed, from billions of years ago. We see these craters because the moon doesn't really have an atmosphere. The moon is also mostly in a vacuum, and so there's no erosion. There's no plants growing on the surface of the moon. There's no water flowing down the surface of the moon to break down the material, and so the craters stay there for a long time. But here on Earth, it's actually really hard to find very old craters, especially smaller ones, because our Earth is constantly recycling the rocks. Rocks are being subducted down into the mantle of our planet. Mountains are forming, rivers are forming, and they're washing the mountains down to the ocean. Rain is coming down and eroding stuff. There's plants growing, worms go into the soil and dig burrows. Sloths, thousands of years ago, dug burrows in the soil. So our Earth is constantly being cycled and tilled by processes, both living and non-living. And so we've actually lost a lot of those really ancient signs of some of the larger impacts. Now that said, we've actually had some pretty big ones. The one that formed the Chicxulub impact, the crater off the coast of Mexico and caused the end of the dinosaurs, was probably about 6 miles or 6.5 miles across. Very big. But we definitely have signs on Earth of some other ones that are very old as well. For instance, one of my favorite is called Vedrafort. It's in Africa. You can look it up online, the Vedrafort impact crater. What's really cool about this one, it was so big that when it hit the Earth and pressure went down into the Earth and then came back up again, and it took a bunch of the interior mantle material and shot it up in the middle of the crater and made a giant mountain. Now it's been so long since that formed that the mountain itself is now eroded back down, but we actually see inside of this structure, it's a giant ring from the crater, and in the middle is a giant ring from the mountain that wore down. But the rocks inside of that mountain, they don't match the other rocks around because they're rocks that were formed from inside of the Earth and are a much different kind of rock. And so it's a really cool place for geologists to study. Now, as far as the largest asteroid, I actually do not know offhand. I'm pretty sure Ceres, but you know, we have a few asteroids that are very large. They're so large, they actually have pulled themselves together into big spheres, or for some of our audience, oblate ellipsoids, much like our planets. And so those are dwarf planets. And things like Ceres and Vesta, Pallas, and Juno, there was actually a time back in the 1890s, if you were in school in America in a little one-room schoolhouse, you might have been taught by your teacher that there were 12 planets in our solar system. But we didn't know about Neptune or Pluto when this was happening. Well, Neptune, 1870s, but Pluto, we didn't find until the 1930s. And so some of those early planets that we had were actually things like Ceres and Vesta and Pallas and Juno, some of these very large asteroids, because at that time, we didn't actually know that there was an asteroid belt. We just thought that they were other planets kind of in between Mars and Jupiter. That's a really great question, but it's also worth looking into. I mean, we're finding more stuff all the time. And I honestly think that in the next few decades, we're going to find out a lot more very large stuff exists in our outer solar system as well.
Amazing. And so we are coming up to 8 o'clock. So if anyone needs to go and take care of whatever, you're welcome to do that. We are going to stick around, I think, for another 10 minutes or so, as long as Dr. Lau has time. And I'm going to post that link again to Ask an Astrobiologist if you'd like to check out more of Dr. Graham Lau. And yeah, so those of you who have to leave, thank you so much for joining us. Those of you who can stick around, type your questions in the chat. We have a question.
I see one right now, actually. Jessica P has asked, are rocks radioactive? And if so, why? Oh, this actually comes from Aubrey, age 11. So Aubrey, yes. many rocks are radioactive. So like I mentioned, there's other kinds of radioactive stuff out there. And there's actually radioactive stuff inside of our bodies. It's all around us all the time. And in the ground at our feet, these rocks, we actually use radioactive materials, radioisotopes inside of things like my meteorite here to tell us how old those things are. I mentioned that we know how old those calcium aluminum inclusions and how old those chondrules are. That actually, we measure that using these radioisotopes, we call them. There's radioactive stuff inside of these rocks. And there's certain places in the world where there's actually a bit more. Some places get an enrichment in uranium or even potassium that's radioactive, other things that are radioactive. And so here in Colorado, we actually have a lot of uranium. Colorado was a very popular place for uranium mining for a long time. We also were a place of storing uranium in the process of making nuclear weapons and making uranium cakes for pellets for nuclear power plants and things like that. And so we actually have a lot of uranium in the rocks here in Colorado as well. But like I mentioned earlier, you're safe. We are entirely safe. We have radiation around us all the time. There's radiation from the sun and from the rocks at our feet and even from the stuff that we eat. But we exist in this environment, and we have for a very long time. It's really when you have extra radiation that you have to be very careful. So like astronauts, if they go to Mars, there's a lot more radiation at the surface of Mars than there is here on Earth. And so astronauts going to Mars have to be very careful. It's not just in the rocks at their feet. It's not just coming in from the atmosphere like it does here. There's a lot more of it. And so we have to find ways to shield them from that radiation. But that's a very fun question.
And I'm just going to jump in and take one question. There was a question about whether DMNS will be doing any programming for the Artemis launch. And yes, we will. But you'll just have to keep an eye out on our website and things, because they haven't like nailed down a specific date for the launch. So as soon as that happens, we'll have some sort of programming. If it's during hours when the museum's open, it'll probably be on site in Space Odyssey. But yeah, keep an eye on our website.
Yeah, it's a very good question. So it was supposed to be December, and even the February timeframe, we're not quite sure. Like I mentioned, they have to do a lot of tests on the spacecraft now before they're allowed to launch it. They have to do these integration tests, they're called, to make sure that the space capsule and the rocket are actually talking to each other the right way, and that they'll actually stay together during launch. There's a lot of other really important tests that have to happen on the spacecraft. There won't be any people inside of the spacecraft. Like I mentioned, it's uncrewed is the word for that. But it's still very important that we do all of the checks the same way that we would if humans were on board as well. Oh, I see a question from Erica Jaffe here. Erica wants to know how I got interested in studying space. And would I go to space if the opportunity presents itself? Well, for your second question, yes. I have been a longtime dreamer and fan of space, and I would love to go to space. And now that it's becoming more accessible in different ways, there's more companies coming online who are offering different kinds of tickets. It's still very expensive, but there are becoming new ways to go to space. There's new companies with orbital or suborbital balloons, suborbital launches, and then also orbital things as well. My friend Cyan Proctor, she was recently a new astronaut on the Inspiration 4 mission from SpaceX. They went higher than humans have gone since the Apollo missions. They went really, really far, way beyond the International Space Station and the Hubble Space Telescope. And she created art when she was in space and took some really cool pictures of the Earth, and really inspired me a lot to think that it could still be possible for me. And so there's a lot of hope still going to space. But I will say, I don't know when I very first got interested in space. I know as a kid, I loved looking up and seeing the stars. I loved watching Star Trek, and I loved playing video games about aliens and space and that kind of stuff. But I do know the moment I decided I wanted to be a scientist. I was 5 years old, and my parents took me to see a movie, and this is quite some time ago. This was 1988. My parents took me to go see a movie called Young Einstein. It was a comedy film with a bunch of really cool 80s music in it. But in the film, there's a character who's a fictitious version of Einstein. And this character inspired me to want to be a physicist. He inspired me to want to learn mathematics, to learn about physics, to learn about people like Albert Einstein and Isaac Newton, Stephen Hawking, other people who've thought a lot through time, to get involved in our attempts as humans to better understand how the universe works. And so maybe it was that kind of drove me more towards science in general. And then along the way, I just got really into biology and chemistry, geology, astrophysics, all of these different sciences. My PhD is in geology, even though I also have a background in biology, chemistry, and astrophysics. But I honestly, I consider myself to be an astrobiologist more than anything.
Very cool, very cool. So we have a few more minutes, so if you have more questions, put them in there. We had a question early on. Is the Earth getting bigger or heavier thanks to all the stuff that's crashing into our atmosphere?
That's a really good question. And up until a few years ago, I might have said that we are constantly gaining some weight because we constantly have stuff falling on the Earth. 40,000 tons, by the way, is an estimate. We haven't measured it directly yet. We have some measurements from satellites and things like that. We have other measurements based on how much we can observe, and then our knowledge of the space environment. And so that 40,000 tons per year is an estimate. And it could be a lot less or a lot more, but it's a good estimate, we think, right now until we get better data. However, that said, so 40,000 tons a year is falling on the Earth, but there's also some other things happening. So for instance, and don't be scared, but we are slowly losing parts of our atmosphere to space. So some of the air that we breathe is actually going into space from our atmosphere all of the time. And this is perfectly normal. It happens to planets. It's part of why Mars actually lost its atmosphere. So we have a really nice magnetic field around the Earth, and that actually keeps our sun from stripping away our atmosphere much faster. And so our atmosphere is actually just slowly leaking, whereas a world like Mars lost its atmosphere, most of it, long ago because of that stripping away. The sun took all of its atmosphere away and it was lost to space. We are similarly slowly bleeding a little bit of hydrogen and oxygen, water into space every year, but we're actually bleeding a fairly substantial number. Nothing compared to the mass of our atmosphere, but it's still enough that there's some current estimates that we might actually be losing something like 10 to 50,000 tons of material every year. Even though we're getting a lot of stuff dropping on us, we're also losing some as well. And so right now, the current science is that we are slowly losing mass from the Earth. But there's a lot for us to learn and discover. There's always measurements to be made and new scientific hypotheses to be made about how much stuff is agglomerating on us, how much stuff is being lost, how much stuff is being broken down from matter into energy, and how much of that energy and heat is being lost into space. But right now, the current science is that we're losing weight.
Right, wild. And what do astronauts eat in space?
Oh gosh, so much stuff. So I remember when I was a kid, we were told like, it's astronaut ice cream. It's all freeze dried, and there's only ice cream and a couple of things they can eat. But honestly, astronauts eat everything. They eat so many different kinds of foods in space. The important thing for them is to try to conserve the amount of material they take to space. So the astronauts get meals that are very nutritious. They're very dense in calories with a lot of nutrients because they want to have to take less material into space. It costs more money to send more material to space. So most of the food is freeze dried, and then it has to have water added back to it. It's called reconstituted, and then they can eat it. But they have all kinds of different foods. There are people whose sole job is to be a space chef to figure out how to make better food for astronauts. They've made all kinds of desserts and different entrees. Just about everything that we eat on Earth, astronauts have eaten. They've had pizza and spaghetti dinners. They've had special celebratory meals. Oftentimes, they'll send special meals for holidays and things like that for the astronauts to eat. Really, they can eat just about everything that we can eat. It's changed a lot from the days of Gemini and Mercury and Apollo. Nowadays, they can really have a whole bunch of different kinds of food. So if you go to space, don't worry. There's a good chance your favorite food can go along with you. It'll most likely be very nutritious and packed with calories. And one thing that's very interesting, it's not as big of a deal nowadays that astronauts will spend a lot of time in space. So like on the International Space Station, when they're there for a very long time, they get accustomed to something really funny that happens. When they first go into space, and this happened a lot with the space shuttle and our early astronauts, they reported that because it's apparent weightlessness, it feels like zero gravity. All of the fluids inside of their bodies are moving everywhere. There's no gravity pulling stuff down. And the way that your sinuses work and the way that your sense of smell works actually relies on gravity and for you to be standing on the Earth. And what happens in space is all the mucus kind of goes up into their sinuses and into their noses, and it actually hinders their sense of smell a little bit. And because of that, for the first several days, sometimes weeks, most of the astronauts report that they can't taste things as well and they can't smell things as well. It's kind of like they have a small cold. And so one thing that the folks who make food for astronauts have done to help with this is they will give them spicier foods, foods that have a bit more flavor to them to help them still taste the food and have that pleasure of eating. Because when you're working in a really dangerous environment like that, one thing that can really help you psychologically and to feel better is to eat good food. It's something that we've done as humans for a very long time. When people would go out on long sea voyages, if you ever have a chance to go travel to the high Arctic or Antarctica, I've done the high Arctic myself. I can say that like having some nice special snacks along is really important for keeping up your morale and just feeling good when you're in a very remote, dangerous kind of place.
Nice. Yeah, excellent. I even heard that the Korean American astronaut was able to bring kimchi to the space station. So
yeah, kimchi's a good
anything's
one.
possible.
Yeah.
Now, so we are getting down to the end of our program. Do you have any final thoughts you'd like to leave everyone with?
Yeah, so like I said, I love to share pictures of the Earth in my talks. I'll share something else really cool with you. This is a patch from my organization. My friend Sanjoy Som has argued for some years that the astronauts, when they go to space, they really should wear a patch. Instead of having the American flag or the Russian flag or the Chinese flag, they should wear a patch that symbolizes our Earth and all of us humans, all of our friendly animals, our fellow plants, everything else that lives on this planet with us really is what we should symbolize, because we are the extension of the Earth going into space. And so his recommendation was a flag of the Earth going into space. And I think it's a very compelling idea. Amongst our audience, maybe some of you also want to go into space and learn more about space exploration, astrophysics, things that we're finding in other galaxies right now. There's so much to learn out there. But one thing you'll discover if you start going down that road and learning more about astronomy is that you start learning a lot more about our world. You start learning and caring a lot more about our planet. There's even this thing called the overview effect. It's this idea that when astronauts go to space and they see our Earth from space, they feel a shift in their thinking about what it means to be human, about what it means to be from a planet that is separated from this vacuum, this void of space, by just that very thin atmosphere. And many of them report they feel a need to come back and make our world better because of it. And so I think one thing we all could use is a little bit of that overview effect, that thought for each other, that, you know, we all want to get ahead. We all want to make money in our lives and be successful and have people get to know us. But we also we can lift each other up. We can lift up everything and everyone from our planet and make our world a better, safer place to live. And I think a big part of that is the experience of space exploration. And so I thank all of you for joining us tonight for 60 Minutes in Space. I hope you enjoyed some of the things I had to share. Like I said, we could do 60 Minutes in Space every day and still have lots of material. There's always so much stuff in space. So please stay curious and keep looking up.
Wonderful. Well, thank you so much. This was wonderful. We'll be back with 60 Minutes in Space on a Tuesday, November 30th next month. We hope to see you all again. And thank you again, Dr. Graham Lau. That was really wonderful. And good night, everyone.